There are a few common Taylor series that you might be expected to be familiar with, and those series consist of the series for e to the x, the series for sine x, the series for cos x, and the series for 1 over 1 minus x. And I'm going to derive all of the formulas for the Taylor series for these four, and I'm going to try to show some context where you might be able to apply them in answering questions. So in general, just to recap how we would find a Taylor series in the first place. The first step is to just make a table consisting of n, the nth derivative at x, and the nth derivative at our desired center value. So for this video, for the sake of all of these series, we're centering them at 0. So our c value here is going to be 0. But in general, if you were to make this table, let's say we wanted to center it at 3, then we would have this column be the nth derivative at 3. But for the sake of this, we're centering at 0, so that's going to be 0 for all of these examples. Then the second step is to find a general expression for that third column, for that nth derivative at your center value. So in this case, we're going to find a general expression for our nth derivative at 0. And then our final step is just to plug it in to our formula. And so for the sake of this, we're basically going to be using the formula for a Maclaurin series, which is a Taylor series that's centered at x equals 0. So it's going to end up being, I'm going to write t at x equals the sum from n equals 0 to infinity of the nth derivative at 0 divided by n factorial times x to the n. So this is our general formula. It's really for a Maclaurin series that we're going to be plugging things into. So the first example that we're going to go over is e to the x. So how would you find the Taylor series for e to the x? So the first thing we're going to do is we're going to create that table of values. So we're going to compare n to the nth derivative at x to the nth derivative at 0. So let's pick some values of n. Let's go 0, 1, 2, 3, ... And what do we know about the nth derivative of e? Well, if we take the first derivative of e to the x, it's going to equal e to the x. If we take the derivative of that, then it's also going to equal e to the x. If we take the derivative of that, then it's also going to equal e to the x. And no matter how many times you take the derivative of e to the x, it will always be e to the x. And so for the first column here, or for the first row here, sorry, the 0th derivative of anything is just itself. So the 0th derivative of e to the x is e to the x. Now if we take the derivative of that, it's going to be e to the x. If we take the derivative of that, it's going to be e to the x. If we take the derivative of that, it's going to be e to the x. And no matter how many times we keep taking this derivative, it is always going to be equal to e to the x. Now what does this look like when we plug in x equals 0 for our third column here? So let's plug in x equals 0 to our nth derivative at x. Well, this is going to end up being e to the 0. This will be e to the 0. This will be e to the 0. This will be e to the 0. And again, no matter how many times we keep taking the derivative, no matter which value of n we choose, our nth derivative at 0 is always going to be equal to 1. And so that's our general expression, our step 2. Our general expression for the nth derivative at 0 is just going to be 1. It's never going to be equal to anything that isn't 1 because it always ends up being e to the power of 0 no matter what, so it will always be 1. So now let's take this and let's plug it into our formula for the Taylor series centered at 0. So we can say e to the x is going to be equal to the sum from n equals 0 to infinity of the nth derivative at 0 over n factorial times x to the power of n. And now we've just found this numerator here. We know what the nth derivative at 0 is. Our expression for that is 1. It's always going to be 1 no matter what. So we can set this equal to the sum from n equals 0 to infinity of 1 over n factorial times x to the n, which is really just the sum from n equals 0 to infinity of x to the n over n factorial. And this is your Taylor series centered at 0 for e to the x. So this is the first one that you should be able to remember. Now, the next one that we're going to go over is the series for cosx. So let's start off by making our table the same way that we did last time. So let's have a column for values of n, one for the nth derivative at x, and one for the nth derivative at 0. So let's pick values of n. Let's go 0, 1, 2, 3, 4, ... And so the 0th derivative of cosx is just the function itself, which is just cosx. We know that the first derivative of cos is negative sine. And then from that, we know, well, the derivative of sine is positive cos, and this is just a constant in front, so we end up with negative cosx as our second derivative, so negative cosx. And then since the derivative of cosx is negative sine x, and we have a negative out here again, what we end up with here is that those two negatives cancel, and we end up with negative sine x, which is just positive sine x. And the derivative of sine x is positive cos x, and then this cycle is just going to continue. It's going to start back up here, it's going to go down through all of these functions again, and that's just going to repeat indefinitely as n approaches infinity. So let's plug in 0 and see how this behaves. So cos 0 is our first term at n equals 0, and that's equal to 1. Then we have negative sine 0. Sine 0 is 0, and negative 0 is just 0, so this is equal to 0. Then we have negative cos 0. Cos 0 is 1, and negative 1 is our answer for this one. Then we have sine 0, which again equals 0. Then we have cos 0, which is equal to 1. So what we see happening here is we have a bit of a pattern forming that we can recognize to make our general expression. So all of our even terms of n equals 0, n equals 2, n equals 4, are alternating between plus and minus 1. And all of our odd terms of n at n equals 1 and n equals 3 are just equal to 0. Now remember that a series, ultimately, is just an infinite sum. So if I sum terms, for example, if I were to sum 1 plus 2 plus 3 plus 4, if I add zeros anywhere inside this sum, it's not doing anything to my final result. The zeros aren't contributing anything to this sum because they're adding nothing. So we can take out the zeros from this expression to try and consolidate it a little bit and simplify things. So let's ignore our odd terms for now. Let's pretend they're not there, and let's try to make a general expression just using the even terms, the even n terms, like n equals 0, n equals 2, n equals 4, etc. So looking at these terms, they're always equal to 1, right? But the only thing we have changing is that it's equal to positive or negative 1. Whenever we have an alternating sign in a series, we know we're either going to need a negative 1 to the n term, or we're going to need a negative 1 to the n plus 1 term. Now, which one of these we choose depends on whether or not we start off positive or negative. Since our first term at n equals 0 is positive 1, we want it to start off positive when n equals 0. So let's plug in n equals 0 to this, and let's plug in n equals 0 to this. Well, this would just turn into negative 1 to the power of 0 plus 1, which is negative 1. That would make our first term negative. We don't want that. So this one here, if we plug in 0, is negative 1 to the 0, which is just equal to 1. This is what we want. So we know that we need to use negative 1 to the n. Now what else is going on here? Well, nothing really. It's just equal to 1 all the time. So all we have is a 1 that's changing signs. So really our general expression for our nth derivative at 0 is just negative 1 to the power of n. So now we're ready to go back and plug this into our general formula. So we can say cos x is equal to the sum from n equals 0 to infinity of the nth derivative at 0 divided by n factorial times x to the power of n. And we just found our expression for the numerator here, so it's the sum from n equals 0 to infinity, and let's plug in our expression, which was negative 1 to the n, divided by n factorial times x to the n. Now, we have a problem here. Remember how we ignored these negative terms? Well, if I were to plug in n equals 1, n equals 3, n equals 5, this term here and this term here could still be negative. Or it could still be odd, sorry. And we don't want that to happen. We want to make sure that no odd terms appear in our expression here. We can still plug in odd values of n here no matter what, since we're just incrementing 0, 1, 2, 3, 4, 5, however you want. But we need to make sure that inside this expression itself, we want it to never be odd. So how can we do that? Well, what if we took all of the n's in this expression and we replaced it with 2n? So let's try the sum from n equals 0 to infinity, negative 1 to the n, over 2n factorial times x to the 2n. Now the reason we didn't replace the n on this negative 1 term is because we reasoned out how we need this to behave at n equals 0, at n equals 1, etc. And we're still plugging in n equals 0, n equals 1, n equals 2. We just want it to be even in these two pieces of the expression specifically. So the n here is perfectly fine, because we still want it to be positive at 0, negative at 1, positive at 2, etc. So we want it to be positive at 1 and negative at 2 and positive at 4. So what we can do is we can use this like 2n to make sure that our terms inside the expression are never odd. And so this expression you have here is our general formula for the Maclaurin series or Taylor series centered at x equals 0 for cosine x. And notice that no matter what value of n we plug in, it's always going to be even here. And we're basically just going to have alternating values according to the pattern we saw here. So the next series that you need to be familiar with is the series for sine x. And it's going to work very similarly to the one that we just created for cos. So let's start off with the table again. So we're going to have our values of n, the nth derivative at x, and the nth derivative at 0. So let's say n is 0, 1, 2, 3, 4. Similarly to last time, we're going to go through and take derivatives, and we're going to notice a very similar pattern forming. So the 0th derivative of sine x is just itself. It's going to be sine x. The first derivative of sine x is cos x. The derivative of cos x is negative sine x. And then since the derivative of sine x is cos x, and we have a negative sign in front, it's going to be negative cos x here. And then the next derivative, the derivative of negative cos x, well, we know the derivative of cos x is negative sine x, and we have a negative sign out here, so it's going to be negative sine x, which is going to just cancel out to be positive sine x. And this pattern is going to repeat. And now if we plug in our 0 for x here, we're going to get sine 0 as the first term, which equals 0, followed by cos 0, which is 1, followed by negative sine 0, which is 0, negative cos 0, which is negative 1, and sine 0, which is 0. So notice now how this is very similar to what we had happening last time. We have our alternating positive and negative 1s here. But notice how this time, all of the even terms are 0. So this time, in our general expression, let's ignore the even terms and let's only work with the odd terms. So we have our alternating sign again, so we know we need to choose between negative 1 to the n and negative 1 to the n plus 1. So if we're ignoring our even terms, then we're treating this 1 here like our first term. So when we first plug in n equals 0, we want this expression to evaluate to something positive. Remember, we're still plugging in n equals 0, even if our first term is going to ultimately equal 1 when we get rid of our even terms. So when we plug in n equals 0 to each of these, this is going to equal negative 1 to the 0, which is just 1. And this will equal negative 1 to the 0 plus 1, which is going to be negative 1. We don't want it to start negative, so this is the expression we're going to choose. And again, we have nothing else really going on here. We just have alternating positive and negative 1s. So this is really just going to be negative 1 to the n is our general expression for the nth derivative at 0. So now we're ready to plug it into our general formula. So we can say sine x is going to be equal to the sum from n equals 0 to infinity of negative 1 to the n, because that was our nth derivative at 0, divided by n factorial times x to the n. And now we have this problem again where we can plug in even values of n, and this can still be even. But we don't want that. So how can we make it so that these n values within the expression itself can never be even? Well, the way that we can do that is we can replace them with 2n plus 1. This way, at n equals 0, this expression is going to equal 1, and so on. When we plug in any value of n, this expression is always going to evaluate to something odd. So let's make that change. It's going to be the sum from n equals 0 to infinity of negative 1 to the n, and again this n stays for the same reason as it did last time, divided by 2n plus 1 factorial times x to the power of 2n plus 1. So this is your general formula for the zero-centered Taylor series for sine x. Again, very similar to last time, except this time we only want to include odd terms, rather than only including even terms. So the final series that we're going to go over is the series that represents 1 over 1 minus x. And this is really ultimately just a power series as well, or the general formula for a power series. But we know that this only converges for x is less than 1, magnitude of x is less than 1. And if you think back to power series, if you're familiar with it, we know that power series are always of the form a over 1 minus r, and they converge for the magnitude of r is less than 1, and the sum is going to equal n equals 0 to infinity a r to the n. So let's derive this properly as a Taylor series. Let's try it out. So the first thing we're going to do is we're going to make our table of n versus the nth derivative at x versus the nth derivative at 0. So let's have n equals 0, 1, 2, 3, etc. Actually, let's give this a fourth term. Okay, so let's start taking derivatives of this. So the zeroth derivative of anything, we know, is just itself. So the zeroth derivative here is just going to be 1 over 1 minus x. But what's the first derivative? Well, the first derivative of 1 over 1 minus x is just equal to the derivative of 1 minus x to the negative 1. So by chain rule, the first thing we're going to do is just take the derivative of the outside and not touch the inside. So that's going to be negative, not touching the inside, 1 minus x to the negative 2. And now let's worry about the inside. So we have to multiply this by the derivative of the inside. The derivative of 1 minus x is negative x. Negative 1, sorry. And we're going to multiply it by negative 1. So in the end, what we're going to end up with is positive 1 minus x to the negative 2, which is just 1 over 1 minus x squared. So let's put that into our chart, 1 over 1 minus x squared. And now if we take the derivative of this, so the derivative of 1 over 1 minus x squared is going to end up being 1 times 2 times, or over 1 minus x to the power of 3. So let's write that in here. 1 times 2 over 1 minus x to the power of 3. And what if we take the derivative of that? Well, the derivative of this is going to end up being 1 times 2 times 3 divided by 1 minus x to the power of 4. So let's add that to our chart. We're going to have 1 times 2 times 3 divided by 1 minus x to the power of 4. And what if we take the derivative of this? Well, I think you might see the pattern forming. We're going to have 1 times 2 times 3 times 4 divided by 1 minus x to the power of 5. So hopefully you see the pattern forming here. If not, we're going to go through it in just a second. But it's important to just look at it and try to acknowledge what you see happening even before we plug in our center value, because it will give you some clues about what's happening when we do plug in the center value. So looking at this, we can kind of see an n factorial forming in the numerator, because we're multiplying all of these successive numbers as we increase our n. And we can also see that in the denominator, we seem to always have a 1 minus x to the power of n plus 1. right? Here it's 5 when n equals 4, so it's n plus 1. Here it's 4 when n equals 3, so it's n plus 1. And we can see that throughout all of them. So now let's go ahead and plug in 0. Well, our denominator is always 1 minus x to the power of something. What happens if we plug in 0 to this expression? It's just going to become 1 to the power of something, which is always equal to 1. So when we plug in our zeros here, it's actually just going to make the denominator equal to 1, and basically reduce this so that the only thing that we have here is really the numerator. So this is going to be 1 over 1, which is just 1. This is going to be 1 over 1, which is really just 1. This is going to be 1 times 2 over 1. This is going to be 1 times 2 times 3 over 1. This is going to be 1 times 2 times 3 times 4 over 1. And you can see the pattern forming. So really, what we have here is n factorial. That's our general expression for the nth derivative at 0. Here we have 0 factorial, which is 1. Here we have 1 factorial, which is 1. Here we have 2 factorial. Here we have 3 factorial. Here we have 4 factorial, and so on. So really, our nth derivative at 0 is always going to be equal to n factorial. So now we're ready to plug this back into our general expression. So we can say 1 over 1 minus x is equal to the sum from n equals 0 to infinity of the nth derivative at 0 over n factorial times x to the n. And we just found our numerator here, so let's plug that in. It's the sum from n equals 0 to infinity of n factorial over n factorial times x to the n. And these cancel each other, so we're left with the sum from n equals 0 to infinity of x to the n. And that is your general zero-centered Taylor series for 1 over 1 minus x. So now I'm going to go over some examples where knowing these formulas might be helpful to you. So what if I asked you to find a Taylor series for e to the negative x? How could you do this? Well, you can recognize that e to the negative x is essentially e to the x if x were to be equal to negative x. So really we can do kind of like a u substitution. So we can say, let's say u is equal to negative x. Well, we know that in general, the series for e to the u is going to be equal to the sum from n equals 0 to infinity of x, or should I say, in this case, it would be u to the n over n factorial, because we've just replaced x with u. And now if we sub in our u, all we're really doing here is replacing x with negative x. We can say that e to the negative x is equal to the sum from n equals 0 to infinity of negative x to the n over n factorial. Now, this is a correct answer, but this isn't often how you'll see it written. Most people will tend to break this up, and they're going to do so using exponent rules. So let's take a look at the numerator here. We have negative x to the power of n. How can we break this up using exponent rules? Well, negative x to the n is really equal to negative 1 times x, and all of that is raised to the n. And when we have everything raised to an exponent like this, we can distribute it inside. So what this is really equal to is negative 1 to the n times x to the n. So let's break it up that way and put it back into our expression. So e to the negative x is equal to the sum from n equals 0 to infinity of negative 1 to the n, x to the n over n factorial. And that's how you'll probably commonly see the answer to this problem written. So for part B, it wants us to find x e to the negative x. Well, we just found this part. We just found e to the negative x. And we're just multiplying it by x. So this is equal to x times e to the negative x. And since we know that the series we just found over here is equal to e to the negative x, this is really just x times the sum from n equals 0 to infinity, negative 1 to the n, x to the n over n factorial. Now, how can we multiply this x into the brackets? Well, we're going to need to manipulate exponent rules again. What is our rule for when we multiply two things that have the same base? Well, in general, this is going to be equal to the same base raised to the power of both exponents added. So if we multiply x by x to the n, we're going to end up with x to the n plus 1. So we can use that here to bring this x into the expression. So this is going to be equal to the sum. That was terrible. It's going to be equal to the sum from n equals 0 to infinity of -1 to the n, x to the n plus 1, divided by n factorial. And that's your answer for that problem. So as you can see, you can basically multiply in anything into your expression from a known expression, and you can also kind of do substitutions for x to kind of have a shortcut to find these otherwise relatively complicated to find Taylor series. For example, if you wanted to do this manually, you'd end up taking successive derivatives of x e to the negative x, which would not be fun. So this is definitely a faster way to remember how to do these problems. Now, what if I told you to evaluate these expressions? How would you go about doing it? So let's take a look at A first. What does this look like that we've just kind of talked about? So we have a 2n plus 1. In the numerator and denominator, we have things that are being raised to the power of 2n plus 1. We also have this 2n plus 1 factorial down here and this alternating term out front. So this kind of looks like our series for sine x, which we determined to be the sum from n equals 0 to infinity, -1 to the n, x to the 2n plus 1, divided by 2n plus 1 factorial. So how can we get this expression into the same form as our sine x expression so that we can use sine x to evaluate it? Well, we can do some manipulation using exponent rules. We have something in the numerator here that's raised to the 2n plus 1, and we also have something in the denominator. Ultimately, our goal is to figure out what this x is, and our x is going to be raised to the 2n plus 1. So how can we consolidate these two expressions into one thing that's raised to the power of 2n plus 1? Well, first things first, let's get the -1 to the n over 2n plus 1 factorial out of the way. And we're multiplying this by pi to the 2n plus 1 divided by 3 to the 2n plus 1. Now what can we do with our exponent rules to this expression here? Well, if we have a over b to the power of c, it's really equal to a to the power of c over b to the power of c. And we can use this rule backwards to consolidate this into one expression. So what we really have, and sorry, this should be a sum, is the sum from n equals 0 to infinity, this should be from n equals 0 to infinity as well, of -1 to the power of n divided by 2n plus 1 factorial times pi over 3 to the power of 2n plus 1. And now we've achieved our form of sine x, where pi over 3 is x. So really, all this is this is equal to sine pi over 3. And we know how to evaluate that. We know that this is √3 over 2. And that's how you get your answer for part A. So now let's take a look at part B. Well, we have something very similar going on here, but this time we have a 2n in the numerator and denominator. We're raising things to the power of 2n. We've got our 2n factorial, and again, this alternating term. So this kind of looks like our series for cosx, which we determined to be the sum from n equals 0 to infinity of -1 to the power of n, x to the power of 2n, divided by 2n factorial. So now we need to use exponent rules again to kind of finesse this expression into this form. So what can we do to consolidate things so that we have some single value of x to the power of 2n? Well, we can do exactly what we did last time. Here we have a pi to the 2n and a 6 to the 2n. So let's consolidate those. So our series is really equal to the sum from n equals 0 to infinity of -1 to the n over 2n factorial times, well, we have a pi to the 2n and we have a 6 to the 2n. So it's really pi over 6 to the 2n. And now we have our expression for cos x, where x is pi over 6. So all this really is cos of pi over 6. And we know how to evaluate that. And again, this is equal to √3 over 2. So our answer to both of these is √3 over 2.